Applications that use Valkey are highly latency sensitive, right? And thus, they need the data being accessed to be located at a data center that is close to them to achieve these low latencies. As a result, a common deployment model for Valkey is to have multiple clusters located in data centers that are close to the end application, right? It is common to have data to be computed and written to Valkey in a data center that is different from the data center where they need to be read, right? For example, a batch analytics job may run some complex computations and store the results in Valkey in data center A. Now, this data needs to be made accessible to other data centers across the world. Another type of use case, which is really valuable, is where the data is dynamic and needs to be in sync from all data centers across the world. For example, it can be a global counter of the number of impressions on a social media post or an advertisement. And any engagement across the world will need to update this number in all the data centers, all the Valkey clusters, right? And finally, a very important use case for geo-replication is for applications that need to survive an entire region or entire data center becoming unavailable or having degraded performance. This is commonly referred to as disaster recovery in industry terms. I'm sure most of you have heard of it. In such a scenario, the application will switch over to using a Valkey cluster in a different region. When this switch happens, the data needs to be already present in the new region. Even if the cluster is being used purely as a cache, let's say, and we're thinking, oh, it's fine, the data not being there is not really that big of a deal. Not having any data in the new region after switchover can cause a lot of cache misses and a lot of read amplification to your actual database. Thus, it is always a good idea in these scenarios to keep your data continuously in sync so that your backup data center has warm data. So we have established now that geographically replicating data across data centers is really valuable. So can this be done using Valkey, just Valkey today? You can, of course, have one Valkey cluster that has replicas distributed across geographies. That is possible. However, there are some problems with this. For example, traffic over a wide area network does not behave in the same way, with the same reliability as traffic within the same data center. So latencies increase, and when cluster mode is enabled, gossip traffic will take much longer to propagate, and cluster mode failovers will be harder to detect, take longer to detect, and execute. It will be hard to execute with such high intranode latencies. So ideally, what we want to have is we want independent Valkey clusters in multiple data centers. This is the use case that we are trying to solve for. So they should be able to accept write operations in parallel, but the data should replicate between these clusters almost in close to real time. At this time, there is no native functionality in Valkey for this. The Valkey community has been discussing this as a very sought after feature. And I'm going to talk about that later on. But the GitHub issue is number 512. So now we will present an architecture that allows Valkey clusters across multiple data centers to stay in sync in real time using Apache Kafka as a replication backbone. Before we start diving into the architecture, here are some things I'd like to go over we would like to achieve from the system. So number one, any changes that are made to a Valkey cluster must eventually make their way to the other Valkey clusters, right? So we want them to be eventually consistent within a reasonable time frame, let's say something in the order of seconds. If two clusters are having trouble communicating with each other, which is a classic network partition scenario, the clusters should themselves still work independently. They should be able to serve read traffic as well as write traffic. And then when the network partition goes away, the clusters should converge on the same data. So to achieve this in a reliable fashion, the data needs to be durably persisted in most cases to prevent us from losing the changes if the cluster goes down before they have been geo-replicated. So at this point, I would like to see a show of hands. How many people here are familiar with Apache Kafka? Have used it or have some idea about it? Okay, that's great. So I have a great audience, but I'll still go ahead and give a brief introduction to Kafka. It is a very popular open source project that has an active community just like Valkey. One mental model to think about Kafka is you can consider this to be an abstraction, a distributed system abstraction for an append-only log, right? So Kafka has the concept of a topic, which is a stream of data, and it can be produced to and can be consumed from. And each topic is subdivided into partitions. The leader for a partition can be configured to get acknowledgements from all the other replicas before it actually acknowledges the record that has been produced. This makes Kafka a durable system if configured properly. This provides us with a very useful primitive upon which we can build geo-replication between Valkey clusters. So we'll use Kafka as the backbone. Now let's take a brief look at this diagram to explain how Kafka works. So the producer is an application that writes records to a Kafka topic. The topic here has 2 partitions, each of which has 3 replicas in total. The producer maps each record to the right partition and then sends it to the leader. The leader then stores the record on disk and then sends it across to the replicas to get replicated. The consumer is a separate application that wants to consume the records for a topic. So it repeatedly sends fetch requests to the leader. And in the request, it sends what is the last offset that it has read and what offset it wants to consume from. And the leader gives it all the new records. So this is overview, high-level overview of how Kafka works. And one more thing to know about Kafka is that it also supports replicating topics between Kafka clusters in different regions. So geo-replication is something that Kafka supports through a feature called Kafka Connect. And we are going to make use of that in this architecture now. OK, I feel like now we have introduced all the pieces needed to build this architecture. Let's take a look at it. The client application that needs to access Valkey talks to a proxy service. This is a stateless proxy service. And in the case of read operations, for example, you want to get the value of a key, the proxy service would directly do a read on the cluster. But in the case of write operations, it actually produces a record to the local region's Kafka topic and acknowledges the write. And there is a component called the syncer. This component asynchronously consumes records from this topic and then applies these write operations to the Valkey cluster. So as you can imagine, the same thing is happening in another region as well. These 2 regions are now functioning independently as independent Valkey clusters. And this is the magic bit where we use Kafka Connect to replicate the data from region A's Kafka topic to region B's Kafka topic and vice versa. So this way, any data written to the proxy service is produced to the local Kafka topic, but it also makes its way into region B's Kafka topic, and it's consumed by that topic, that region's syncer, right? So let us review what this architecture offers us. The replication between the Kafka topics makes sure that the operations are sent to all regions, keeping the data in sync in almost close to real time. Thus, in the case of an entire data center going down, applications can be configured to use a different Valkey cluster. And we can expect that cluster to be relatively warm with most of the data being present. Because we only acknowledge write operations after durably persisting to a quorum of Kafka replicas, we get a highly durable system. So even if the topics are not able to replicate across data centers for some time because of a network partition, the data and the offsets for Kafka topics are reliably stored on disk. So the Valkey clusters themselves are able to keep on functioning without availability loss. And when the network partition goes away, things converge eventually. So I'll dive into some failure scenarios or some scenarios where things can go wrong and talk about how this architecture deals with it. So what happens when there is a network partition between the 2 data centers? We already talked about this. The cluster keep accepting read and write as usual, and they buffer all the pending changes to Kafka. What happens if the Kafka consumer stops working for some reason, right? There can be any number of bugs in the consumer. So what happens then? So this will temporarily lead to some inconsistencies between the 2 clusters, as you can imagine. But The good thing is Kafka makes it very easy to monitor with the right tooling, very easy to monitor what is the lag between the latest consumed record for a consumer and the latest produced record. So this lag between the two offsets is something we can set alerts on. And if we set the right alerts, we would find out about it early on before the queue builds up too much. So we should be able to set up alerting to find out about this scenario. Now, finally, what happens when a Valkey cluster goes down entirely, right? One good side effect that comes out of this architecture is that it gives us a way to recover most of this data. What we can do is we can restore from an RDB snapshot taken from another cluster in another data center, and then we can replay the Kafka records that have occurred since the snapshot was taken, so we can achieve a final state that looks just like the original cluster. So this persisting operations to Kafka gives us the ability to recover even when the Valkey cluster goes down entirely. We can bring it up in another region. Of course, the trade-offs of this architecture, one of them is that it requires us to run the proxy and the syncer outside of Valkey. This naturally leads to some complexity in the architecture, right? We have to maintain more infrastructure. Then because of all the write commands are intercepted before they actually make their way to Valkey, we can only support a subset of commands for which the effects of the command can be determined from the command itself, right? So this serves most of the use cases. For example, you can do a set, you can do a hset, you can do an sadd. These are fine, but there are some subset of Valkey commands. Take spop, for example. What does spop do? Spop is going to randomly pop an element from a set. So if we replicate the spop command to multiple clusters over Kafka, then the problem is that it will end up getting processed by individual Valkey clusters, and they are going to pop different elements in each of these clusters. So the final data does not look like the same in all the clusters, right? So the way Valkey deals with this natively in its replication is that it will first randomly select an element that needs to be popped, and then it rewrites the spop command as an srem command. So it deterministically says remove this specific key, specific item from the set, and then replicates the srem command. So we can do something similar in the proxy to bridge this gap. And finally, one more trade-off is that if changes happen to the same key in multiple clusters almost at the same time, there is no deterministic way to break the tie and choose the same winning operation in all the clusters. That is because we are functioning outside of Valkey and we don't have access to all the data to know who should win the tie in all scenarios. So I think this is a great time to talk about how this can be achieved natively in Valkey without any dependency on other software. I would like to use this opportunity in this conference to kickstart the discussion about implementing this in Valkey itself. Building it in Valkey has the advantage that we can replicate effects of the commands and not just the intent of the command themselves. This will allow us to support many more commands, just like spop, which I mentioned above. Doing this in Valkey would allow additional metadata to be stored per key. For example, you can store a timestamp of when the key was last updated or any other sort of notion of time. This timestamp can then be passed around during replication and can be used to decide the winner deterministically in the case of conflicts. This is a common way to implement last writer wins semantics, and this is used in many other databases. Finally, there are popular operations in Valkey that support conflict-free semantics. For example, incrementing an integer value or adding an item to a set. If an integer is incremented by 3, let's say the number 3 in data center 1 and is incremented by 5 in data center 2, then we can merge the two operations so that eventually, after both the operations have been processed, data center 1 and 2 both have incremented the integer by 8. So CRDTs are a group of data structures that can be used to achieve this when we are building this natively in Valkey. So that was my presentation. I would love to keep this conversation going in the community on how we plan to build this natively in Valkey. You can reach out to me on Slack or catch hold of me after this talk, or we can keep conversation going on the GitHub issue thread that is listed here.